So we will restart from this very pretty movie that we saw yesterday. As I said, this is a movie of a flare. The flare is simply this brightening of this region that you saw. So this is real data captured from the sun, from the solar corona, and this image is at a wavelength of 195 angstrom, which is in the extreme ultraviolet part of the spectrum, and this represents roughly a few million degree Kelvin plasma, which can be found only in the upper reaches of the atmosphere, which is the corona. So this brightening is the flare. So this is a sudden brightening in 195 angstroms, but experience tells us that this such large flares or brightenings observed all across the electromagnetic spectrum. Okay, and these little white dots that you see on the screen, these are signatures of accelerated particles, massive particles, not photons, particles with mass, such as alpha particles, protons, things like this. Right. So and just to sort of give you a context, this is really a very small part of the solar surface. It would be something like if this is the solar surface, you are really seeing a blow up of just this. Okay, this is what you're really seeing, like that. So you're just seeing a blow up of a very small part of the solar surface, and what you're really seeing is this. You can kind of make out, but it's not very evident. What you're really seeing is a sequence of very twisted loops and so on and so forth, and something is happening to those loops, which causes, you can see some of these loops, something is happening there, which causes the onset of this flare. And as we have suspected many times, it is really at the heart of this violent energy release, and also smaller energy releases, some examples of which we have seen before, is the process of reconnection, which is essentially a process of facilitating restructuring of magnetic field lines that were stressed, and they like to relax. Why are they stressed? As we said yesterday, it's most likely because of differential rotation. You have magnetic field lines embedded in the solar corona, say a magnetic field line like this. Now the problem here is that the higher latitudes, say suppose this was the equator, okay, lower latitudes move faster than higher latitudes. So this leg moves fast, and this leg moves slower. Okay, so naturally you can imagine that this loop, this is a magnetic field line loop, right? So this loop will not remain like this simply because of the fact that one leg is moving faster than the other. It starts getting twisted, and when it starts getting twisted, it acquires it has more energy, as in as in the amount of energy that is stored in the twisted magnetic field loop is larger than the amount of energy in this lower energy configuration. This would be almost a potential field configuration, and the process of reconnection helps these stress fields relax. And in reality, of course, the field lines are not as simple as this. They are considerably more complicated. Okay, right. So now let's take a step back, and I also told you that these kinds of flares are often accompanied by bodily ejections of plasma, which are called coronal mass ejections. We will come to that, but before that, let us talk a little bit about why we should care about, why should we care about solar eruptions. Well, one of the reasons is, of course, it's a very nice lab. It's an excellent astrophysical lab to study, fluid dynamics and plasma physics, and these processes of magnetic reconnection are happening at a grand scale. So simply from a scientific curiosity point of view, it's pretty cool. But there is a practical aspect to it also, and I thought I would spend a little bit of time talking about this practical aspects, which is generally called the Sun-Earth connection. And so let us do that right now. Now, as I said earlier, we are really well immersed in the extended solar corona, not our atmosphere per se, but because the magnetosphere shields us. As we know, the Earth has a magnetosphere, and charged particles, which is what the solar wind comprises of, do not like to cross magnetic fields. So in a sense, the Earth is surrounded by a magnetic shield, and so our atmosphere, the air we breathe, is well below the magnetosphere. But nonetheless, the Earth as a whole, the Earth system as a whole, including the magnetosphere, is very much immersed in the extended solar corona. Okay. Now, but it's not as if the solar wind is nice and steady all the time, although those were the equations that we solved. Okay. There are occasional transient disturbances in the solar wind. The word transient means, something that is not steady state, that is not, it's blubby. Okay. So there are transient disturbances of the solar wind, such as the sun spitting out a considerable portion of its corona. Okay. It's as if it takes some of its upper atmosphere and throws it out. It spits it out along with the magnetic fields and plasma and everything out into the general heliosphere. And of course, it's not every time that these ejections reach the Earth. And these kinds of things are called coronal mass ejections, CMEs, for the C here and the M here and the E here. Okay. And the largest of these CMEs are invariably accompanied by bursts of photons, which are visible across the electromagnetic spectrum. We just saw a very beautiful example, and they're called flares, right? And these coronal mass ejections sometimes head towards us, not always. Okay, it depends upon the geometry. But some of these coronal mass ejections can head towards us. I mean, towards Earth. This is what I mean. Okay. And these coronal mass ejections, they are magnetized, okay, and they carry magnetic fields with them. And the Earth also has a magnetic field shielding it, the magnetosphere. And so the interaction between these two magnetic field lines, if they are oppositely directed, we now know that oppositely directed magnetic fields, when they come very close together, they can reconnect. And so if that happens, their interaction with the Earth's magnetosphere, it does a lot of things to the steady state configuration of the magnetosphere system. It's fairly complicated what happens, but by and large, this interaction of the CME with the Earth's magnetosphere comprises what's called a space weather transient. Okay, and what is it? Well, these transients, so what are these space weather transients? Well, these transients are essentially characterized by anomalous, I emphasize the word anomalous, as in anomalous meaning out of the ordinary. I mean, as in the plasma in the immediate vicinity of the Earth, just above our atmosphere, say the ionosphere upwards, it has a certain steady state configuration. Okay, and when these coronal mass ejections interact with the Earth's magnetosphere, things happen, and there are out of the ordinary disturbances in all plasma parameters, such as the plasma density, the energetic particle flux, magnetic fields, current, so on and so forth. Lots of things. Okay, and also changes in the magnetospheric field configuration, and they can cause. Okay, so they can cause a variety of disruptions in technologies, both space-based as well as ground-based. That we know we are very dependent on space-based technologies these days, such as the cell phone that we use. Dish TV, it communicates with satellites, Earth orbiting satellites. So if the atmosphere in which the satellite is operating, if the density, magnetic fields, currents, and so on and so forth in that atmosphere changes suddenly, the operations of that satellite will be hampered greatly. Okay, and these things are generally because of charged particle or current excess outside of the magnetosphere, accompanying day-side reconnection, day-side meaning the side of the Earth that's facing the sun, and fairly complex processes on the opposite side, on the night side. Okay, so These things, these space weather transients, have a variety of effect. It affects astronaut safety. For instance, if you were conducting a human space flight, or for instance you were conducting a spacewalk or something, say on the International Space Station, you needed to send an astronaut out to repair something or something, you need to be very, very conscious about their safety. They are wearing these safety suits, but nonetheless, if there's an expectation that there's going to be a large space weather event, then this is so to speak bad weather for the astronaut. Okay, this is almost certainly fatal. So you should be very cognizant of that. Changes in the density or energetic particle flux or so on and so forth around a satellite, it affects the drag experienced by the satellite, and most of the time it enhances the drag, and so it reduces its life, so on and so forth. These space weather transients can cause disruptions to space communications. For instance, if you're communicating with a satellite from the ground, like the dish TV that you use, or so many other instances, GPS, for instance, GPS signals are transmitted from the ground to the satellite, and the satellite sends us back. So these communications can be disrupted due to space weather transients. And of course, anomalous entry of charged particles of cosmic rays into the Earth's atmosphere, which result in anomalous currents in the atmosphere, discharges, which so on and so forth, lots and lots. And GPS, I've outlined this in red because it's very, very important to us in everyday life these days. Okay, the global positioning system is something that's of importance, not only for instance, if you're using Google Maps or something, but also to guide aircraft navigation. When an aircraft is landing, you need the GPS, you rely heavily on the GPS, so on and so forth. It also often causes power grid outages. These things, of course, power grid outages and things like this are especially more severe at higher latitudes, latitudes that are closer to the pole. The purpose of this slide was not to explain the space weather transients in any great detail, because it's a very complex subject, somewhat outside of the purview of the course, but just to give you a bit of a bird's overview of the kinds of effects that transients in the solar corona, in other words solar eruptions, can have on our everyday lives. Okay, so these are some practical reasons to wonder about what's causing these solar transients and how these solar transients propagate and things like this. So apart from a basic physics viewpoint, where it's really curiosity based and it's cool to study them, it's very nice to understand them. Apart from that, there are also practical reasons to understand them so that we can predict and we can mitigate the effects of these space weather transients better. If we understand them better, naturally we'll be able to mitigate their effects better. Right. So here are some examples of recent large space weather events. There was a power grid blackout in Quebec in Canada and a large parts of the northeastern United States in March 1989. 2 Canadian satellites were disabled in January 1994 because of space weather transients. And then mind you, each satellite is really, really expensive. Okay, these are like go up to millions of dollars. So it happens that Canadian satellites were disabled, but satellites launched by any country, they're in outer space. Outer space simply means outside of the immediate Earth's atmosphere. They're still pretty close to the Earth. These things called geomagnetic storms very much affect Earth orbiting satellites. Okay, so 2 entire satellites disabled. This is a serious loss. Okay, and the Mars probe was hit by solar energetic particles. This is a short form for solar energetic particles that were emitted during the course of one of these eruptions, like we saw in the movie, these white specks. So these are called solar energetic particles. because of a rather large geomagnetic storm in January 2005. Lots of airline paths had, especially the ones which are flying over the North Pole, these paths had to be diverted. So regular airline paths have to be rerouted, and this is a major thing. You have to have lots of coordination. It causes considerable changes in schedules, and also it's a big business decision because it impacts the profitability. I mean, you change an airline path, you make it longer, it consumes more fuel, and so on and so forth, and so the flight is costlier. That's what it is. So and there were several outages of GPS and the global positioning system due to a series of especially large events, several especially large events in October and November 2003. And historically, perhaps one of the largest flare coronal mass ejection event happened in August and September 1859, and interestingly, the Geomagnetic Observatory in Alibag near Bombay, this recorded, this was one of the few observatories which recorded this event called the Carrington event. And there were also very large events recorded in 1882, May 1921, August 1972. These are, so to speak, record breakers, so to speak, okay, record setting events. Just to say that these are examples of large space weather events, and here is a paper that I was part of. That's me here, and this tells you how, due to a space weather event, there was a transient weakening of the Earth's magnetic shield. So there was a chink in the Earth's magnetosphere, so to speak, and this weakening was probed by a cosmic ray instrument situated in Ooty, and so this was published in the Physical Review Letters in 2016, just an instance. Okay, so from our point of view, this was a very quick run through of various effects that can arise due to space weather events which are caused by eruptions on the sun. Let's sort of consider this in a little more detail. What causes these events? Okay. Most of the time these are due to coronal mass ejections from the sun. And what are these? As we've mentioned before, these are bodily expulsions of coronal plasma. Okay. And so million degree coronal, same thing. Coronal plasma is about 1,000,000 degrees hot. It's not like it's uniformly 1,000,000 degrees. It comprises multi-thermal plasma. Some of the constituents are considerably hotter than 1,000,000 degrees, about tens of million degrees. But nonetheless, 1,000,000 degree plasma is a good estimate to go by. So these are expulsions of 1,000,000 degree plasma, and they're quite occasionally accompanied by flares. And flares on coronal mass ejections, different things. Okay, flares are just bursts of photons, whereas coronal mass ejections are actual bodily expulsions of this coronal plasma. And these coronal mass ejections, or CMEs, are often aimed at the Earth. Okay, so let me now show you some examples of CMEs. Here is an example. So what this is, I have to explain this figure a little bit. What this is, you see the sun. This is a series of juxtaposed movies. Okay, the sun is in the very center. Okay, and so this is just an image. This is an extreme ultraviolet image of the sun that's just artificially superimposed on this picture. What this is a picture of is really this black disk that you see. This is what's called an occulter. Okay, this particular instrument which took the red image and the blue image, these are what are called occulters. Okay, they create artificial eclipses. You see, an eclipse happens when the moon comes in between the sun and the earth, and so what happens is the moon blocks the face of the sun. And the face of the sun is very, very bright, which is why you're not able to see the surrounding corona, which is much dimmer. So what this occulter does, this is a space-based occulter. It's sitting on a spacecraft and it blocks the face of the sun somewhat like this. Okay, so this is called this instrument is called a coronagraph. So this black circle is one such occulter. Okay, and so this occults the sun up to a distance of about 2.2 solar radii. Okay, so this, where my cursor is right now, is about 2.2 solar radii, and the edge of this red field of view is about 6 solar radii, if I'm not mistaken. So from 2.2 to 6 solar radii, you are able to observe the corona, and as the movie runs, you can see out here that there is an expulsion of some white bright material which is like going out, and this is what is a coronal mass ejection. This bright stuff, it means that you have excess density over and above the surroundings. Okay, so that means that there is some excess density of coronal material, because coronal material is what you're seeing right now, that is expelled outwards. Okay, so this is one coronagraph which is imaging the sun from about 2.2 solar radii to about 6 solar radii, and this blue stuff is yet another coronagraph which is imaging the sun from about 4 solar radii all the way up to this. The edge of this field of view is about 30 solar radii. So taken together, these two instruments are giving you an uninterrupted view of the sun. These two coronagraphs are giving you an uninterrupted view of not the sun, the solar corona, from about 2 odd solar radii all the way up to 30 solar radii. And what are you seeing in this movie? You are seeing a coronal mass ejection which is propagating outwards like so, and you see it continues in the outer field of view, and you can see that the white stuff continues outward. So this is an example of a coronal mass ejection, and this was also accompanied by a flare. A flare would be brightening somewhere here that you're not able to see that, but you know, trust me, it did happen. And the telltale signatures of that flare are these white streaks that you see. These are massive particles, as in particles with finite mass like protons, alpha particles, and so on and so forth, which were accelerated in the flare, which are now hitting the detectors, and you're seeing these streaks. These are essentially ionization streaks on the detector which is observing these coronal mass ejections. So this is one very nice example of a coronal mass ejection, and here is yet another example. You see this particular thing only has this is a bit of a close-up, and it's showing the field of view is only from about 2.2 solar radii, which is the edge of this occulter, up to about 6 solar radii. And here too you can see that there is bright stuff. Yeah, you see this bright stuff here, and actually these are three coronal mass ejections. There was one going off that way, there was one going off this way, and there's one going off here also. And this happened on January 19th of 2012. Okay, so several coronal mass ejections happening all at once. And I will save the best for the last. Here is another truly spectacular movie of a coronal mass ejection. Now let me explain this a little bit. These are two spacecraft. Okay, these are images from two spacecraft, one here and one here. Okay, there is one spacecraft which is obtaining these images. There is one spacecraft which is obtaining this image, and there's another spacecraft that's obtaining the right pair, this image and this image. So the pair of spacecraft that are obtaining this and this and this and this, these two spacecraft are what are called the NASA stereo spacecraft, for obvious reasons. Two spacecraft imaging the sun, earth, the heliosphere in tandem, just like our two eyes, which always see in stereo. Okay, the way this image is structured is that, you know, whatever is being seen by the left spacecraft and the right spacecraft is folded out and laid on a two-dimensional piece of paper. That's why you see the earth here as well as here. If we were able to see this with two eyes, what this would actually happen is that the brain processes it and it folds up the left image and the right image into a three-dimensional image. Here this three-dimensional image is projected onto a two-dimensional plane. So now what is this showing us? This is showing us a coronal mass ejection which is going all the way from about, this is about 30 solar radii, this is I suppose about 50 solar radii, and this is 215 solar radii. That's sun earth distance, and we see a coronal mass ejection which is propagating like so, all the way, and you can even trace it, although it becomes dimmer and dimmer and dimmer, and therefore it's progressively more difficult for the instruments to detect it. You can see this coronal mass ejection coming from the sun and coming all the way to hit the Earth. And you can see the same phenomenon as observed by the other spacecraft, and in this case too, you can see the coronal mass ejection propagating and coming all the way to the Earth. So you can rest assured that everything that we've been saying about space weather transients and so on and so forth is not just fiction. Here is an actual demonstration, this is real data, of a coronal mass ejection which is propagating from the sun, comes and reaches all the way to the Earth. Of course, what this doesn't show you, when the coronal mass ejection hits the Earth and when it causes geomagnetic storms and so on and so forth, well, that's what we talked about here. So to summarize as a grand summary, I would say everything that we've been talking about by way of magnetic reconnection and so on and so forth, magnetic reconnection is at the heart of solar eruptions. Solar eruptions like flares and coronal mass ejections. And we've seen why it's important to study flares and coronal mass ejections, because we can learn something about this cool process of magnetic reconnection, but B, also because it has considerable practical relevance. Many of these coronal mass ejections, they are responsible for large transients in the near Earth space environment, which affect range of technologies that we depend upon in our daily lives. And at the heart of all this is this process of magnetic reconnection. Okay, of course, there's also this other thing. It's all a fluid phenomenon. Once the coronal mass ejection gets ejected, the manner in which the CME propagates from the sun to the Earth, this is, it's a viscous medium. The solar wind, although it's a collisionless medium, it's a viscous medium, so it's subjected to viscous drag. We've talked about viscous drag early on in the course. So all of these fluid phenomena, in particular magnetohydrodynamic phenomena, can be brought to bear in study of at least this one particular astrophysical context, which is that of the solar corona. So I thought I would go into some detail, simply because it's very immediate and we can appreciate the practical relevance, and also the solar corona in the sun as such is a great lab for studying these fundamental fluid dynamical and plasma physical aspects. Many of these things can be studied in terrestrial labs on the Earth, but these are stages where such processes can be pictured and envisaged in much more grandeur than what's possible in laboratories on the Earth. So with that, we will stop here. Thank you very much for your attention.